Okay, we're going to be integrating using trig identities. So hit pause, let's get the lesson objective down. Once you've done that, hit play and we'll go straight to an example. Okay, so let's have a look at this example here. Find the following integral. So I'm looking for a standard differential that gives me tan squared x, because I want to integrate tan squared x and reverse the differentiation. Now, there isn't one, so is there some way I can rewrite tan squared x? Is there an identity using tan squared x? Well, I think there is. Now, the way I remember it is I use the trig identities I'm comfortable with. Sine squared x plus cos squared x is equal to 1. I'm happy with that. Now, if I want to get tan squared, I need to divide by cos squared. Dividing through by cos squared, I get my tan squared x plus 1 is equal to, c is going to be the third letter, so sec squared x. That means tan squared x is equal to sec squared x minus 1. So, is there an integral of sec squared? There's one there. So if I differentiate tan squared, I get sec squared. Happy days. So I can say that the integral of tan squared x with respect to x is equal to the integral of sec squared x minus 1 with respect to x. When I integrate sec squared, I get tan x. When I integrate 1, I get x plus my constant. That's job done. So it's about finding the right trig identity that I can integrate. Okay, I can integrate sec, go back to tan. Hit pause, copy that example down. Once you've done that, hit play, and we'll look at another. Okay, so let's have a look at this example here. Integrate the following. Integral of 3x cos 3x with respect to x. Now that looks very much like one of the double angle formula to me. Now I don't remember them all. Instead I just remember the basics. I know that sine of a plus b is equal to sine a cos b plus cos a sine b. So if b equals a, then I get sine of 2a is equal to sine a cos a plus cos a sine a. That means sine of 2a is equal to 2 sine a cos a. Okay, in this case a is equal to 3x, so if we say let a equals 3x, then we can sub back in here. So we got sine of 2 times 3x is equal to 2 sine 3x cos 3x. And so sine 3x cos 3x is going to be a half of that then. So therefore sine of 3x cos 3x is equal to, divide by 2, a half sine 2 times 3 is 6, so 6x. Okay, so we can sub that back in the original integral. So we can say the integral of sine 3x cos 3x with respect to x is equal to the integral of a half sine 6x. With respect to x. I can integrate that, because if you remember from last week what we were saying, we've got to think about what we differentiate to give us sine, and that's going to be cos, but cos gives us minus sine, so this is going to be equal to, it's going to be a sixth of the dot means times, 6th of a half, and it's going to be minus, let me put a minus here, minus cos 6x plus c, which is equal to minus a 12th of cos 6x plus the constant. Okay. Hit pause, copy the example down. When you're ready, hit play again. We spent more time trying to find out something that we can integrate than the actual integral, because once we've got something we can integrate, then it's pretty straightforward. Right, hit pause, copy this example down. When you're ready, hit play. We'll look at another. Okay, let's have a look at this example here then. What have we got? Integrate sec x plus tan x squared with respect to x. So let's expand the brackets and see what we've got. So we've got integral of sec x plus tan x all squared with respect to x. That's going to be equal to sec squared x plus sec x tan x plus tan squared x. Okay, so I can integrate sec squared x. I can also integrate sec x tan x. I can't integrate tan squared x, which was the first example we looked at, but we can change that. Oops, got my integral sign here, brackets, and with respect to x. So let's see what we can do with sec squared x is fine. Let's forget the c, plus sec x tan x plus, now if you recall what we said about tan squared x, we had sine squared x plus cos squared x equals 1, and we divided by cos squared x, because sine over cos is tan, plus 1 equals the third letter, so sec squared x, which meant that tan squared x is equal to sec squared x minus 1. We can sub that in here for tan squared x, so that's going to be sec squared x plus 1. Oops, sorry, minus 1, I tell a lie, minus 1. With respect to x. So that's going to be the integral of 2 sec squared x plus sec x tan x minus 1 with respect to x. And now we can integrate. So sec squared is tan x, so it's going to be 2 tan x plus sec x tan x gives us sec x plus sec x plus x. Oh, not plus, I've done it again. Minus x minus x plus the constant term. Okay, so hit pause. Let's get this example down. Once you've done that, hit play, and we'll look at one more example. Okay, in this example, we've got to integrate sec x plus tan x all squared with respect to x. Well, first things first, what we've got to do is expand the brackets. So we're going to expand the brackets out, see what we've got then. Okay, so the integral of sec x plus tan x all squared with respect to x. If we expand the brackets, we get sec squared x plus 2 sec x tan x plus tan squared x. And that's the integral with respect to x. Okay, well, when I want to integrate that, I can integrate sec squared x, that gives me tan x. I can also integrate sec x tan x, that gives me sec of x, or sec x, and tan squared I can't integrate because of the first example we did. We had a bit of trouble integrating that, so we changed it. Remember, we did the sine of x, sine squared x plus cos squared x is equal to 1. We changed this identity. In order to get tan, we divided by cosine, cos squared x, all the way through. So that gave us the tan squared x we were looking for. Plus 1 is equal to cosine, so c is going to be the third letter, sec squared x, which meant that sec squared x, tan squared x is equal to sec squared x minus 1. So I can sub that for tan squared x. It's going to be the integral of sec squared x plus 2 sec x tan x plus, instead of tan squared x, we go sec squared x minus 1 with respect to x. So if I combine the sec squared, that's the integral of, oops, I forgot my brackets there, integral of 2 sec squared x plus 2 sec x tan x minus 1. Put my brackets round with respect to x. So if we integrate term by term, I integrate sec squared x, I get tan x, or 2 tan x. If I integrate sec x tan x, I get sec x, so that's going to be plus 2 sec x, and integrate 1, get x, and don't forget our constant. Okay, hit pause, copy that example down. Once you've done that, hit play, and we'll look at one more example. Okay, so let's have a look at this example then. Got to show this time, so it's a proof. Show that the left hand side equals the right hand side. Show that the integral from pi by 12 to pi by 8 of sine squared x with respect to x is equal to pi by 48 plus 1 minus root 2 over 8. Okay, right. First things first, I want to integrate, I'm going to look at the left hand side. So taking the LHS, I want to integrate sine squared x with respect to x from pi by 12 to pi by 8. Okay. Now I can't do that straight off. I don't have a differential that gives me sine squared x. So I'm going to look at the double angle formula. Now I don't remember the double angle formula, but I want to find sine squared. So I'm going to use this one, cos of a plus b, which is equal to, if you remember, cos a cos b minus sine a sine b. Okay, so if b is equal to a, then we get cos of 2a is equal to cos squared a minus sine squared a. I know cos squared is equal to 1 minus sine squared minus sine squared a. So cos 2a is equal to 1 minus 2 sine squared a. I want to get the sine squared a on its own. So if I flip it over this side here, I get 2 sine squared a is equal to 1 minus cos 2a. And if I divide by 2, I get my sine squared a. Sine squared a is equal to a half minus a half cos 2a. Okay, so now I know that sine squared is equal to half minus a half cos 2. So I can sub in here then, from pi by 12 to pi by 8. And I've got a half minus a half cos 2x. I'm going to integrate that with respect to x. Okay, so now I can integrate term by term. If I integrate a half, I get a half of x. If I integrate a half of cos 2x, then I get minus a half, because instead of 2x I need to half my differential, if you remember from last lesson, times the half that already exists there. This is a half sine 2x from pi by 12 to pi by 8. Okay, so now what I've got to do is sub in for pi by 12 and pi by 8. So I'm just going to move my equal sign over here, give myself a bit of room. And that's going to be the integral of a half times pi by 8. The dot means times. You can use brackets if you would like. Minus a quarter sine 2 times pi by 8 minus a half of pi by 12 minus a quarter of sine of 2 times pi by 12. Okay, let's try and simplify this. So we got pi by 16 minus a quarter sine of pi by 4 tell you what, I'll leave the brackets off now. So minus pi by 24 plus a quarter of sine pi by 6. Okay, so let's collect like terms and simplify. We've got pi by 16 minus pi by 24 minus a quarter sine of pi by 4 plus a quarter pi by 6. Sorry, sine pi by 6. So the common denominator here is 48, which is great because that's what I'm looking for. So out of 48, I got times 3, so 3 pi minus times 2, 2 pi. That's great because that gives me my pi, so I've got to sort out the rest. Minus a quarter, sine of 45 is 1 over root 2 or root 2 over 2 plus a quarter, and sine of pi by 6, sine of 30 is a half. The dot means times, by the way. So we end up with pi by 48, which is perfect, minus root 2 over 8 plus 1 over 8. Okay, so I'm going to flip them round to make it look like the question we got there. So it's equal to pi by 48 plus 1 over 8 minus root 2 over 8. And if I just use the 8 with one common denominator, I'm done. It's pi by 48 plus all over 8 1 minus root 2. That's job done. Exactly what I was looking for. So hopefully that wasn't too bad. It's all about finding out what you can integrate. Okay. These are given to you in the booklets in the exam. So hit pause, copy this down. Once you've done that, I've got a couple of exercises for you to go through. Excellent. Okay, so exercise 11C. You could go down the left-hand side of the page. That'll work. But if you're not sure by the time you finish question 1, maybe you should be looking at a couple of other questions then. Okay? Okay, good. Good luck.